Here's the final part, part 3 of the entire grade 12 calculus course. We're going to look at derivatives of trig, exponential, and logarithmic functions in this section. So let's just start with finding some derivatives with respect to x for these types of functions, and then after that we'll do a couple applications. So this is an exponential function. The derivative of an exponential function equals, you keep the power exactly as it is and multiply that by ln of its base. So the derivative of 10 to the x equals 10 to the x ln 10. For this function, y prime equals, same type of thing, it's an exponential function, so you keep the base, 4 to the power of 3x squared, multiply that by ln of the base, but because in the exponent I have a function that's differentiable as well, I need to differentiate 3x squared and multiply this by that as well. So I have this whole thing times 6x. So that's the derivative of this function. Part C, 2x plus 3e to the x. So I can differentiate each of these terms completely separately. So the derivative of 2x is 2, plus the derivative of 3e to the x would be equal to 3 times the derivative of e to the x, which would be e to the x ln e, but ln e is 1, so I don't need to write that factor. Right? The derivative of e to the x is just e to the x. Part D, I have a product of two functions, so I'll need product rule, and I forgot to name it, so I'll call it y. When using product rule, I have to differentiate the first function, so 4x cubed, multiply that by the second function, 2 to the x, plus I have to differentiate the second function, which would be 2 to the x ln 2, multiply that by the first function, x to the 4. And when we use product rule, we should check to see if we can simplify it by taking out any common factors between the two terms. So I've got a term here separated by a plus sign, and then I have to look for any common factors between the two terms. They both have the same power of 2 to the x, and they both have factors of x. This one has 3, that one has 4, so I could take out an x cubed and a 2 to the x from each term. And then what I'm left with for this term when I common factor this out is just a 4, and what I'm left with this term, I'm left with one of those x's and ln 2, so x ln 2. Part E, now I have some trig functions. Keep in mind the derivative of sine is cos, the derivative of cos is negative sine, derivative of tan is secant squared. So when I differentiate these, y prime equals, so the derivative of 3 sine x would be 3 times the derivative of sine x, which is cos x, so 3 cos x, plus the derivative of cosine is negative sine, so negative sine, keep the argument as it is, and then use chain rule to multiply this by the derivative of its argument. So multiply that by 2. And I could just simplify this a tiny bit. 3 cos x, I've got a negative 1 times a 2, that's negative 2. So I can write that as minus 2 sine of 2x. Part F, when I differentiate tan, I know the derivative of a tan function is equal to secant squared of the same argument. And then chain rule then tells me I need to multiply this by the derivative of the argument, which is 3. So I could just rewrite this as 3 secant squared of 3x. Part G. Once again, it's an exponential function. So y prime equals, it would equal negative 2 times the derivative of this exponential function. The derivative of 10 to the 3x would be, you keep the same power, 10 to the 3x, multiply by ln of the base, and then multiply that by the derivative of the exponent, right? That's based on chain rule, so I need to multiply it by 3. And then I could simplify a couple of these factors here. The negative 2 times the 3 is negative 6. Part H. When I find the derivative of this, it might be helpful actually to rewrite the function knowing that this cubed means that the sine x squared function is being cubed. So sine x squared is being cubed. So I just rewrote the function. So now that I can see I have a power of a function, so I'll need chain rule. I'll bring the exponent of 3 down as the coefficient, leave the base exactly as it is, reduce the exponent by 1, and then chain rule says now multiply that by the derivative of the inside function, so by the derivative of the base of the power. The derivative of sine of x squared would be cos of x squared times 2x, right? That would have to be multiplied by chain, I have to do chain rule again, I have to multiply it by the derivative of the argument, which is 2x. So that gives me 3 times 2x is 6x, and I've got a sine x squared squared, I could write it as sine squared of x squared, and then I have to multiply that by a cos of x squared. So there's the equation of the derivative for h. I. More trig functions. Y prime equals 2 sine, so I need to differentiate 2 sine x, that would be 2 cos x, minus 3 times the derivative of cos of 5x, which would be negative sine, keep the argument the same, use chain rule, multiply by the derivative of the argument, which is 5, and then I could just collect the factors of 3, negative 1, and 5 together. So y prime equals 2 cos x plus 15 sine of 5x. Part J, y prime equals, well notice here I have a trig function where the argument is another trig function. So I'm going to need chain rule. I'll differentiate the outside function with respect to the inside first. So derivative of sine is cos, keep the inside function exactly as it is, and then multiply that by the derivative of the inside function. So multiply it by the derivative of cos x squared, which I'll need chain rule for again. It would be negative sine of x squared times the derivative of the argument, so the derivative of x squared is 2x. And then there's nothing much to simplify here other than I have a factor of negative 1 times 2x, that's negative 2x for part J. Part K, this is our first log function we're doing the derivative of. So when I do the derivative of a log function, y prime equals, we'll have to do 4 times the derivative of this function, so 4 times the derivative of a log function. The derivative of a log function is 1 over, you take the argument, write it as the coefficient, multiply that by ln of the base of the log. So multiply that by ln 5. And then what I could do here is I could multiply the 4 into the numerator. To simplify it a bit, I get 4 over x ln 5. So let's give this one a shot. This one we'll need chain rule for because the argument here I could also differentiate. So let's see how that works. So y prime will equal 1 over, you take the argument, 4x squared, multiply that by ln of the base. If you don't see a base, that means you have the common logarithm, which means the base is 10. And that needs to be multiplied by the derivative of the argument. So multiply that by 8x. And then I could simplify this a little bit because look at these factors. I have 8 divided by 4, that's 2. And this x can cancel with one of those x's. So my final answer here, I've got 2 over, right, 1 times 2 is 2, 2 over x ln 10. Part M, another log function, but this time it's the natural log function. It's ln. So when I differentiate this one, it's actually slightly easier because I do the derivative of any log function is 1 over, the argument becomes the coefficient, so x cubed plus 3x, times ln of the base. But you notice I didn't leave room to write it because I need to multiply this by ln e, but ln e is just 1. So this is just the derivative. But then I have to multiply this by the derivative of the argument, right? I have to use chain rule because the argument of the original ln is a function I can differentiate as well. So I need to multiply this by 3x squared plus 3. And that could just move into the numerator. Y prime equals part n. So this one is the first one where y isn't explicitly written in terms of x. So I'll have to use implicit differentiation, right? Y is not isolated. If you want a more detailed explanation of implicit differentiation, make sure you check out my video on that because I'm not going to be able to go into full detail for this one. When I differentiate this, I have to differentiate all of this with respect to x. So I'm going to start with this product. So I'll need product rule. So when I differentiate this, I'll have to do the derivative of x squared, which is 2x, times y, plus the derivative of y. The derivative of y with respect to x, well, I'll just write that as dy over dx times x squared. Plus, now I need the derivative of this product. Well, this one, I have to differentiate y squared. Well, the derivative of y squared, I can differentiate that with respect to y first, so that'd be 2y, but then that has to be multiplied by the derivative of y with respect to x, because that's what I actually want. I don't necessarily want the derivative with respect to y, I want it with respect to x. So do derivative with respect to y times the derivative with respect to x. That has to be multiplied by x, keep in mind we're doing product rule here, plus the derivative of x, which is 1, times y squared, equals the derivative of 1, and the derivative of any constant is 0. So now we just have to isolate dy over dx. So I'm going to leave the two terms with the dy over dx on the left, and so this term here and this term here, they're staying on the left, but with that process, I'm going to common factor out the dy over dx from both of those terms. So that would leave me x squared plus 2yx on the left. And on the right, I'll move this term and this term to the right because they don't have a dy over dx. and that gives me negative 2xy minus y squared. And then I can isolate dy over dx just by dividing this factor to the other side, x. So that's how you do implicit differentiation. Let's do two more really quickly. This one's super easy. The derivative of e to the x is just e to the x. This one I'm going to need product rule for. Derivative of sine of 2x would be cos of 2x times 2, so I'll write that as 2 cos of 2x, times e to the 3x, plus derivative of e to the 3x would be e to the 3x times 3, so 3e to the 3x, times the sine of 2x function. And then I'll check for any common factors. Between the two terms that I have, I could take out an e to the 3x from both of those functions, and what I'm left with is 2 cos of 2x plus 3 sine of 2x. Example 14, let's do an application of this. So find the equation of the line tangent to this curve at this point. So here's the graphical representation of what we're trying to find. Here's that f of x function, and what we're trying to do is find the equation of this blue line, this tangent line, that touches the f of x function only at this point right here when x is pi over 3. So to write the equation of this line, we're going to need to figure out its slope by using the equation of the derivative and plugging in pi over 3, and we're also going to need to find its y-intercept by plugging in this point, this xy point, and the slope into y equals mx plus b and solving for b. So if I want the equation of a tangent line, I know I need its slope. So I'll start by finding the slope of the tangent line by figuring out the value of the derivative of the function at pi over 3. So the derivative of this function would be 4x plus the derivative of this term would be 4 cos of 4x. So I'll find the value of the derivative at pi over 3, so y prime at pi over 3 equals 4 times pi over 3 is 4 pi over 3 plus 4 times cos of 4 times pi over 3. And if I want cos of 4 pi over 3, just really quickly, the principal angle 4 pi over 3 is here, with the reference angle of pi over 3. I'm in the tan quadrant based on cast rule, and this is a special triangle with sides root 3 to 1. So cos of 4 pi over 3 equals negative cos pi over 3, which is negative a half based on that triangle there. So I have 4 pi over 3 plus 4 times negative a half, which would be 4 pi over 3 minus 2. So I have the slope of the line. Slope equals 4 pi over 3 minus 2. I now need a point on the line, because in order to solve for the y-intercept of my tangent line, I'm going to need to be able to plug in for x and y. So let's start by finding a point on the tangent line by plugging in pi over 3 to the original function, because I know the tangent line touches the original function at pi over 3. So plug pi over 3 into this function. So 2 pi over 3 squared plus sine of 4 pi over 3. And I can get sine of 4 pi over 3 from this special triangle as well. Sine of 4 pi over 3 would be negative sine pi over 3, which is negative root 3 over 2. So I've got 2 pi squared over, don't forget to square the 3 as well, 9, minus root 3 over 2. So that's the point on my tangent line. My point is pi over 3, comma, 2 pi squared over 9 minus root 3 over 2. Now it's not a nice point, but that is my x and my y. So I can now find the equation of the tangent line by solving for the y-intercept in the equation y equals mx plus b. We'll plug in our y, our x, and our m, and then we can solve for the b value. Now we just have to isolate this for b. I'm not going to worry about making it look nice and simplifying it up. Let's just get a value for b. So I've got 2 pi squared over 9 minus root 3 over 2 equals, I'll distribute this pi over 3 in and get plus b. Move these terms to the other side and collect. Like this will collect with this one. They have the same denominator. And 2 pi squared minus 4 pi squared is negative 2 pi squared over 9. And I've got a plus 2 pi over 3. And don't forget this minus root 3 over 2. I mean, I could get a common denominator for all three of those and write it as a single fraction, but I'll just leave that for now, and let's write the equation of our tangent line. So that's the equation of the tangent line to the curve. Example 15, find the equation of the line tangent to this curve as an exponential function at this point. It actually gives us the y-coordinate this time, so that'll save us a bit of work. Here's the graphical representation of that in Desmos. The red function is our exponential function half to the x, and the green line is what we're trying to find the equation of. the tangent line that touches the function at that point, -3/8. So we're going to need its slope using the derivative, and also we're going to need to solve for the y-intercept using the point and the slope, and then we can write the equation of the line in the form y equals mx plus b. So in order to find the equation of a tangent line, I'm going to need to know the slope of the tangent line at the point where x is -3. So to do that, I just find the equation of the derivative, which is 1/2 to the x ln 1/2, and then plug in the x value of -3 into this equation, and it'll tell me the slope of the tangent at that x value. So let's plug -3. And I know the exponent rule: when I have a negative exponent, I can flip the base and change the sign of the exponent to positive. So I've got 8 ln 1/2. That's my slope. M equals 8 ln 1/2. So that's the slope of the tangent line. And I know the point on the tangent line was -3/8. So that's my point. I've got slope. I can now find the equation by solving for b. So the equation in the form y equals mx plus b. Plug in the y, 8. Plug in the slope, 8 ln 1/2. And plug in the x, -3. And we'll solve for b. So 8 times -3 is -24. Move it over, it's +24. So I've got 8 plus 24 ln 1/2. That's my b value. So the equation, y equals, and that's the equation of the tangent line. And it's an exact equation. Example 16, the last example. The function for a current is I at t equals 9 cos of 120 pi t, where I is the current in amps and t is the time in seconds. There's 4 parts to this question. Part A says find the current when time is 6. We just need I at 6, and I have Desmos calculating that for me right here. The value of the function when time is 6 is 9. So I at 6 equals 9 amps. Part B says the electromotive force, E at t in a circuit, is given in volts by finding the first derivative of the current function. So find the function for the electromotive force. So we just need to find the derivative of the current function. So we were trying to find I prime at t. So let's look back at I at t. It was 9 cos of 120 pi t, so the derivative would be 9 times the derivative of that cos function. So 9 times negative sine of 120 pi t times the derivative of the argument using chain rule, so times 120 pi. And then we could simplify this by multiplying the 9, the -1, and the 120 pi and getting -1080 pi times sine of 120 pi t. So there's my derivative function. That's the electromotive force function. And part C asks us to evaluate the electromotive force when time is 3. So we just want to evaluate E at 3. And we could do this one without a calculator, because if we understand trig functions well, and specifically the unit circle, when I put 3 in for t, I'll get sine of 360 pi. And 360 pi, well, that's a multiple of 2 pi, right? I know sine of 0 pi, 2 pi, 4 pi, 6 pi, 8 pi, those are all 0. So sine of 360 pi is also 0. So I have -1080 pi times 0, which is 0 volts. Part D asks us to find the maximum and minimum electromotive forces and the times that they occur. Well, I could find the max and min using transformations. Let me just quickly rewrite the E at t function again. So E at t equals -1080 pi sine of 120 pi t. I want to find the max and min values of this, so I can use transformations. So the max is equal to the c value plus the absolute value of a, which in this case is 0 plus 1080 pi, so that's 1080 pi volts. And the min is equal to c minus the absolute value of a, which is equal to 0 minus 1080 pi, which is -1080 pi volts. The tricky part with this question is figuring out when do these occur. So I need to set this E at t function equal to those values and solve for t. So I'll do that in 2 parts. I'll do the max over here, and I'll do the min over here. Let's start by solving for the max. Let's start by solving for the max voltage by setting this E at t function equal to the max voltage, which was 1080 pi t. Now let's divide the coefficient to the other side, and we get -1 equals the sine function. And when is a sine ratio equal to -1? Well, if you know your unit circle well, you know that a sine ratio is equal to the y-coordinate of where you intersect the unit circle. And when will we be at a y-coordinate of -1? Well, if the angle of rotation, 120 pi t, is equal to 3 pi over 2, or anything coterminal to that. So 3 pi over 2 or add 2 pi to that, right, because that's the period of a sine function. Add 2 pi to that, I would get 7 pi over 2, or add 2 pi to that, I get 11 pi over 2, or so on, right? All these angles are coterminal. They would all intersect the unit circle at a y-coordinate of -1. So how can I make this input, right? How can I make this angle, the 120 pi t, equal to these? Well, let's isolate t by dividing the 120 pi to the other side, and I get t equals 3 pi over 2 divided by 120 pi, that's 3 over 240. Divide the second answer by 120 pi, I get 7 over 240, and so on. And notice the relationship between each of these answers. They're not 2 pi apart, right? Because the period of this function isn't 2 pi. The period of this function, you do 2 pi divided by the absolute value of k, and this is the k value right here. So the period of this function is actually 1 over 60, which we see represented here by the difference between these values, which is 4 over 240, which is equivalent to 1 over 60. So these are all 4 over 240 apart. So how can I express all of these answers without writing an actual infinite number of answers? Because, right, this keeps going on forever. So we could say t equals, well, the first answer is 3 over 240, but I can add 4 over 240 as many times as I want. And I can represent that with k. And I can combine these and write these as a single fraction, where k has to be an integer, right? It has to be a whole number, but we want to restrict it to 0 or the positive integers, so I would say k greater than or equal to 0. And keep in mind, these are times in seconds, so I should have put my unit of seconds here. So these are all the times where if I were to plug in any positive integer, including 0, into this equation, I would get a time that has a max voltage. So let's go ahead and do the same process and solve for what times the min voltage occurs at. So let's set the t function equal to the min voltage, which was negative 1080 pi. Now let's divide the coefficient to the other side. We get 1 equals the sine ratio, and I know a sine ratio is equal to 1 if the angle of rotation is pi over 2 or anything coterminal to that. So set 120 pi t equal to pi over 2, or add 2 pi to that, and I get a coterminal angle, 5 pi over 2, add 2 pi to that, 9 pi over 2, so on. Now let's isolate t by dividing the 120 pi, and we get, so divide each of these by 120 pi, we get 1 over 240, 5 over 240, and notice these answers are all 4 over 240 apart as well, right, because that's the period of our transformed sine function that we have up here. And these answers go on forever, so let's express all of these as a single answer by writing t equals 1 plus 4k over 240, where k is an element of integers, and k is greater than or equal to 0. And once again, I forgot to write my units. This is in seconds. Alright, that's it for the calculus course. Make sure to go to jensenmath.ca and you can download more of the practice problems, and you can try the actual full exam review and their solution posted there. Alright, that's it.